To the lectures itself, right? So up until this point, we studied about the different kinds of RL algorithm in the sense of how we can classify model-free RL algorithms in particular, how we can classify them as value-based, policy gradient, or actor critique methods, right? We have an overview of all those methods now, how they work, why we need one algorithm over the other, or not over the other, instead of the other rather, right? So we did all this. Up until this point, it was for mostly vanilla RL, that is without deep learning, right? We did not have neural networks or any kind of function approximators. What was the main limitation of using normal RL, that is without reinforcement learning? Sorry, without deep learning? Anyone? Why? What was the main limitation of using reinforcement learning without neural networks or without function approximators? Okay, yes, simple problems. So as the complexity of the problems increase, RL without neural networks or without function approximators might not be able to handle it effectively, right? Exactly, we can estimate the value functions now over more complex planes, implying that we could look into more dimensions, right? Like not just 2 or 3 states, but multiple states and multiple actions. And we can have continuous actions in space, continuous actions and states, right? Because we are using neural networks, we could then look at a more, what do you say, a complex plane, right? A hyperdimensional plane rather than 2 or 3 dimensional plane, and then find the maxima or minima of it corresponding to the optimal policy. Clear up until this point? Okay. So yes, as we talked about, tabular methods or the normal RL up until this point that you studied was effective for small toy problems basically, right? But as the problems get more complicated, especially in the domain of robotics, you need a more advanced paradigm of reinforcement learning and you get that when you fuse function approximators with it, right? Function approximators primarily are neural networks, okay? Oh yes, sorry. This is an important point. So, okay, if you have tabular methods, right? If you have tabular methods, you will have state S1, state S2, state S3, action A1, action A2, action A3, and so on. Okay. Now say there is a state somewhere between S1 and S2. Okay, like say suppose you are discretizing the entire world in increments of 5 degrees. Okay. So your robot can now move at any angle by moving 5 degrees at a time, rotate 5 degrees at a time. So if there is anything in the space of say 11 degrees or a non-multiple of 5 degrees, right? In the situation that you cannot actually, your state space is not covered in that value, then if you're simply extrapolating the values, right? Or interpolating, say you have 10 and 15 and your robot is at 11. So now you can interpolate and get the values at 11, right? But then they will not work as effectively or as efficiently as a continuous space would, right? Hence, this is also a need for function approximators. Okay. Yes, again, so the objective remains the same, that is to maximize the cumulative reward over the entire state space, over the entire episode. And then we will have, okay, yes. Now if you have discrete set of actions, you could use softmax to get the probability for each actions. Okay. However, if your action space is continuous, then you can use Gaussians, right? So there you will get a continuous spread of Gaussian distributions with a given mean and standard deviation, right? With the action corresponding to the mean being the most likely action to be chosen, right? This also helps in exploration. What was exploration again? What is exploration in reinforcement learning? Okay, yes, and why do we do that? Exactly. To not get stuck in a local minimum, right? Now, since we are using neural networks, there or function approximators, there, okay, I will use the terms neural networks and function approximators interchangeably, so pardon me for that if I don't use it correctly. So, okay, because we are using neural networks now, one of the errors that we might face is an approximation error. Okay, what are we doing here? We are approximating the value functions, either the q value or the action state values, the v functions, that is. We are approximating both of these values. Okay, now when we are approximating this using a neural network, we might not get the exact value or the accurate value. Why? Because of the neural network structure itself. Okay, you could end up using a neural network that is not comprehensive enough to completely encompass the complexities of the value functions that you have, right? So say you have to maybe increase the dimensions of it, the size, or the neural network itself, the non-linearities that you use, that might be an issue. So you might have to change that, use different non-linearities. All these combined together leads to multiple errors, right? Estimation and approximation errors. And because there is, remember that these actor critique methods use TD approach for estimating the value function. You remember TD approach in Monte Carlo, right? Sure. Or you need a recap after 1 week. Okay. So you have this TD approaches which rely on bootstrapping, right? What is bootstrapping? Estimating, right? So you are in one state, from there on you estimate the rewards that you might get in the future, right? Which is obviously prone to errors. Now when this accumulates because of the neural networks, these errors might increase, right? Yes, also you have to balance the bias and variance, right? What is bias? Closeness to the actual value that you have. Variance is change in the episodic reward or change episodic estimation, right? You cannot let the episodic estimation change by a lot. Then you will not converge very quickly then. And if your bias is way too much, even if you have low variance, it simply means that the value that you calculated, computed, or approximated is not correct, right? So the entire exercise of computing is of no use, is useless basically, right? So all these errors come into play when we use neural networks, right? Yes.
Like the error is like typically three terms: the bias, the variance, bias related term, and variance related term, and plus irreducible noise, right?
Plus,
irreducible.
yes, there is noise, but we can. That is because of the. Yes, there is noise because of the neural networks itself. True. That will.
Speaking in any kind of learning.
Yes, yes, yes. That's why the approximation error, basically. The approximation error lumps all these errors and it gives you that. It doesn't give you that approximate error. Basically, it causes that error in approximation. So yes, there is noise that you cannot get rid of.
Exactly.
No matter what. No matter what, yes. But then, however, in the coming slides and in the coming lectures, you will see that there are small tricks that are used in order to overcome or at least compensate these errors, right? One thing is to make sure that the learning rate of the critique is higher than the actor. Okay, you want the critique to learn faster than the actor. That is because, say okay, what does the actor in critique do?
The actor does the action.
Okay. Exactly. Okay. So critique evaluates how good or bad that action is by the actor. Okay. Now assume a scenario where actor takes 5 different actions in a given time frame, whereas your critique is slow and it evaluates only, say, action 1. But by that time, the actor has already taken A1, A2, A3, A4, and A5. So it will, the feedback that the actor will be receiving will be for an outdated action. And say the actor is going to take A6 when it receives this feedback, the actor will then think that, okay, fine, that is a bad action I took, the last action that is, and it will try to compensate for that. However, it might be a good action, it might have been a good action, right? So therefore, you need to make sure the learning rate of the critique is more than the learning rate of your actor, okay? The feedback should be faster than the correction, basically, okay? Okay. Yes. Again, like I told, you might face an issue where the optimizer or the RL agent might get stuck in a local minima, right? Because of inefficient exploration, maybe, right? Or simply because of the neural network size being too small, so you don't even reach the states, even with exploration. Say by adding epsilon greedy noise, right? If you add that, you think you might explore everything, but then because of the sheer complexity of the environment that you are in, you might end up missing a lot of states. So there is not enough exploration, which might include the optimal path, right? So all these issues needs to be corrected for, okay? Also, now unstable gradients is something when you have correlated samples, right? Like say it learns in a correlated manner, right? That okay. Okay, I remember giving this example. Say you take a series of action to reach the goal. Okay, if you evaluate the entire trajectory together, you might end up getting an okayish trajectory. Okay, however, there might have been a few actions in that trajectory which were particularly bad, like very bad, which would take you away from the goal. Like say maybe if I'm standing here and if I turn this side, I'm completely moving away from the goal, right? Now if I move forward, I'm going further away from the goal. However, I simply decide to take a U-turn now at this point, okay? Then my overall path is okayish, not very good, but okayish, right? But say if the agent decides to evaluate the entire trajectory in a connected manner and not independent state actions, then you might end up getting a suboptimal policy, right? Because of this correlation, right? So we need to break this as well, right? So in order to do this, there are a few tricks that are done. Also, the learning itself, right? Now, because you have neural networks now, okay, the parameters of the neural network change, which would result, say you have a normal neural network, forget reinforcement learning, okay? You have a normal neural network, you give an input, because it goes through the neural network, that is multiplied by the weight and then added with a bias, goes through a nonlinear function, which is the activation function, passes like this through multiple layers, and then you get output, okay? Now if you change this number even slightly, the input number, because of the way the neural network is, the weights that it has learned or it has acquired, the output might change drastically. Like say suppose you have a neural network that takes in 1.01, the output is 50%. And then 1.03, the output may be 1%. You get it? So because of small changes in input, the output that you're getting changes drastically, right? Now imagine the actor is facing this issue, okay? That is, it takes an action, say torque of 5% of maximum, okay? The output, the motor would rotate say by 10 degrees, okay? In the next episode, the actor is like, okay, now let me try with 6%. 5 to 6, right? But then now the motor rotates by say 88 degrees. It's a huge change, right? Which is too much, right? And you update the parameters very quickly. That could have happened because of the noise itself, right? However, because you are learning, the RL agent will think that, okay, fine, this action is bad. So it will penalize a lot and it will quickly move away drastically from that value, right? So the change between any two consecutive steps will be massive, right? This way we will not get a stable learning curve, right? The gradients will change a lot. You don't want that to happen, right? You want it to be reasonable, because in robotic systems in particular, when the input changes incrementally by very small increments, the output also changes by not too much, right? Now say suppose you have a drone, right? When you increase the thrust, say from 10% to 12%, the drone will fly a little bit. From 12 to 14, it will change a little bit, right? It will not simply go up and hit the floor, hit the ceiling, right? Small increments corresponds to small output changes, right? So these kind of intuitions are important in order to update or stabilize the learning, right? You will see why, or rather how this comes into effect and what we will be doing, okay, in order to overcome or compensate for these issues. Clear? One such trick is the use of target networks, okay? So remember we talked about using actor network and critique network, right? We had one neural network for actor, one neural network for critique. Cool? Now, if, like I said, if there is a scenario like this where a small input changes the output by a lot, then as a reaction to this change, the neural network will very quickly and drastically change its weights, right? And in the next episode, you will realize that no, for 1.04, say the output was 47%. So you realize that this was a noise, right? So because of this, you already changed the weights a lot. Now again, you have to change back the weights by huge number or by a huge value or a huge percentage, right? You don't want that to happen, right? So what you do is instead, you take two copies of neural networks, right? You will have two actors, you'll have two critiques, okay? One pair of actor and critique will interact with the environment, update themselves after every episode, after every step, say after every step, okay? However, the other set of actor and critique networks that you have, also usually called as target actor and target critique, you update them say after 10 steps or maybe 15 steps or 100 steps. That is, you let the main neural network change drastically very quickly, okay? But you update the target networks more slowly. You're more careful into letting it in when you want to change the main actor critique. So after training, when your training is completed, the neural networks that you will be using are the target actor and critique, right? Clear? Eventually you will learn, but it is more stabilized learning, right? You don't let the changes happen very quickly. Clear? Okay, so you use two set of neural networks, say NNA and NNC, set 1, set 2, set 1, set 2. These together are updated more regularly. The other set of neural networks that you have, also usually called as target networks, you update them not so frequently, like say after 5, 10 or n number of episodes to stabilize the learning. Cool?
And you call the second
Target networks.
target,
Yes.
what about the first one?
They're simply actor and critique. They're actor and critique. Okay. Yes.
Basically, the network that will be used for the pair of networks that will be used for training or during the training will be the target network.
Yes. Yes. The other such trick that we use is something called experience replay. Okay. Now, before I move on to this, okay, experience replay, can it be used for both on policy and off policy methods? How many of you think it's applicable for on policy methods? Raise your hands, please. Experience replay can be used for on policy methods. I'll first tell briefly what experience replay is. Okay, experience replay is basically you take a sample. Okay, you remember this tuple, the very important tuple that we talk about very often. May or may not be this. Okay, you have this tuple: state, action, reward, next state, next action. Or rather mostly this. Okay, what does it mean? It means in a given state, you take an action, you see what reward you get and which next state you end up in. Okay? You take these at every step of your training or learning, okay? And you use this to update the parameters of the neural network. Cool? Okay? In experience replay, what you do is you take this tuple, okay, you put it in a bag. You keep stocking it and storing it in a big box, assume a big bag, okay? And later on, say after 100 episodes maybe, you realize that, no, let me break the temporal correlation, or even while training, okay? Say after 500 steps, you realize, no, let me break the temporal correlation. You're like, bring me back that tuple. You bring back that tuple, update your parameters from a tuple from that bag, okay? And then you move on again. You do this to break the temporal correlation that you have, right? Now, can this be used for both on-policy and off-policy methods? Yes?
I think more for policy. When we said before that small sample effect, that we can depend on the like several changes, because on policy I think has a specific sequence.
Right.
Or we edit one part. If we take from like the same tuple or so, it could have a totally different policy. So it will change at all.
Exactly, exactly. Yes.
Say, for instance, that we use for our policy, policy given the term policy, so it's still picture of the previous data.
Exactly. So this method of experience replay is used for off-policy methods only. Okay. The reason being, this tuple that you pick from the bag, okay, might be generated by a policy which is not the current policy that you are following, right? So therefore, that breaks the on-policy assumption. That is, you are following the policy, that you're updating the parameters of your actor and critique by following the policy that you started with, right? So this is applicable for off-policy methods. Okay? Sorry. So what you do here is you store the tuples, okay, in something called an experience buffer, okay, and then after every now and then, after every n steps or whatever steps you have, you take a batch of those samples, okay, 5, 10, 50, whatever. You define all these as hyperparameters in your training algorithms. You take those mini batches, you update your parameters, and then you're like, okay, fine, let's go on again. Yes.
So in this case, neural network use the same
Sorry.
network for both prediction and targeting.
Again.
If you use the same network, not separate, like one for target and one for the update,
Okay.
then it will work or it will not work.
You mean this experience replay thing?
This one, the one, this one is two. Like you use one you update and other one you use for the target. And update one you update for some interval of time to cover up the divergences or instability. If you use the same network both for the updating and for the prediction, then it will work or not.
You mean we eliminate the target networks and use only S1 and S2?
One network for both prediction and targeting, not for the one will be updated separately and other we use as a target. And update one we updated because to remove divergence or instability.
I do not understand it. Again.
If you use same network for both for the
What both?
same neural network
Okay.
for both the prediction and for the target task, like in the previous topic used.
Okay. No. Okay. We have two neural networks here. Okay. Not for different policies. It's simply the rate of update that is different. One set of actor and critique that you have, the one that interacts and gets updated, the update happens very quickly. Okay, and say after a certain predefined number of episodes, what you do is you take those parameters, copy it onto the target networks. Okay, these networks do not have they do not interact with the environment. They are simply updated from the main one after a certain episode, after a certain number of episodes, to stabilize the learning. Is that what you're asking? Right?
So, sir, like I didn't get the concept here. Like, so you say like another part we updated and to get to the target neural we are using two neural networks, one for the neural network to update it to a neural network. Another neural network will, after some policy, we get like this is the target one, and this target one we will update another one to reach to the one.
Okay, I see what you mean. Okay. See, listen. So you have actor 1 and you have critique 1. This together is one set of neural networks. Okay. Now here you have an environment. Okay. These two together will interact with the environment. That is, the actor will take the action obviously and critique will evaluate it. They'll interact with the environment that you have and these parameters are updated. Okay. This happens every step or every episode. Clear? And then you have another box with another two set of neural networks. These neural networks are the target neural networks. Okay. By target, I don't mean that they are trying to reach to a target. Okay. They don't have anything to do with the goal that you have. They simply are updated by this neural network, okay, less frequently than this one. Say this is one episodes, this will be after n episodes, where n can be anything greater than 1. Right? This way, these parameters change less often. Plus, the change itself in the parameters is smaller. That is, the variance is smaller. Got it? This will stabilize the learning.
Learning of the first neural network with environment.
No, with this one.
Which learning it will stabilize?
Okay, which learning it will stabilize? It will stabilize the learning of this neural networks. Okay, now this one, the update is way too fast. Okay, so that is because of the very fast interaction. When you take those enough number of steps and you average the, say, average or whatever, okay, you basically take the updates after given a more number of steps, the update will be more softer. Got it? It will stabilize the learning of this neural networks, not this. This is simply for interacting with the environment. Okay? These are called target neural networks because these are the neural networks that we'll be using at the end. Got it?
About talking about steps and episodes in implementation, usually when we evaluate rewards.
Evaluate?
Rewards.
Okay.
It's something really specifically. Usually it's evaluated to evaluate the system. They are like reward versus time steps or rewards versus episode, each episode. I mean, if you want to see the performance, usually, how you graph it, what are the metrics?
In MATLAB, it's episode. Reward, returns rather with episodes. Return because it's the entire episodic value that you get.
I'm not talking about MATLAB specifically, I mean literature usually.
Time steps as well, you have time step. Okay. So, why does it matter?
To see what is the effect, like where to stop, for example. And sometimes, usually I've seen a method of saving several checkpoints of weights after a specific number of time steps.
Yes.
And actually, the last checkpoint might not be the best.
Absolutely.
Other ones.
Absolutely.
So like when evaluating, for example, the case I'm saying, it saves every 10,000 time steps.
Okay.
It saves the 333 episode or something because the frequency is
Right. Okay.
around
Okay.
this.
Okay.
I mean,
Okay.
when I plot every checkpoint reward to see which one I would like use later or so, or like plot the full time steps and then choose the area that I see in the highest reward, like continue or so.
Okay. Yes. Okay. That's an interesting thing. Listen. So, suppose you have rewards with time steps. Okay. Time steps now. Your reward will keep changing like this. Okay. And it will stabilize like this. Okay. Now, if you see the limits or the intervals you have for the time steps will be in some multiple, which would then end up this being one episode, this being one episode, this being one episode, because you cannot stop the update mid episode, that is when the task is not completed, and you use that as your final weights, right? So this time steps, the point at which you're getting the reward should correspond with the end of the episode. Okay.
Every point is the return after the end of like several episodes.
Several episodes. No, one episode.
One episode.
One episode, yes. Now you will see that it will not always be say this will not be 0, 5, 10, 15, 20. Okay, even I mean this axis will be like that, okay? But you will see rewards not exactly corresponding at 5 or 10 or 15. Why? Because there are certain episodes, because of the termination condition, which will end prior to the maximum number of time steps you have. Say in one episode, maximum you have 100 time steps. Okay, but because of your terminal condition, the episode terminates at 88 steps. Okay, so here you will not see a value at 100 time steps. You will see a value at 88 time steps. Okay, similarly, now because these are time steps which are accumulated, your next episode may end at 100 time steps. So now your next point will be at 188. You get it? That's why that's the reason why I think MATLAB has it in episodes. Because then it's easier. Then you will have 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it? Clear? Okay. Okay. Now, from today's lecture onwards, I will be talking a lot about practical considerations as well, because from now onward, it's more about implementation. Okay. Theory part is mostly done. Okay. So you need to understand in terms of implementation how you do it. Okay. So one such thing that you have to be very careful of is to normalize the inputs and preferably even rewards if you can, okay? Because say you have a system where there are 3 inputs, okay? One has a scale of 0 to 1, the other has 100 to 1100, the other has -5 to +70, okay? Got it? Now, you see the range of these inputs, they're very different. Okay? Now, neural networks, when it is updating, neural network doesn't understand the physics. It doesn't understand that this is, say, the angle may be in first quadrant, second quadrant, third quadrant. No, it will not. It will simply see it as numbers. Right? So when it is seeing numbers, it will treat this as number, this as number, this as number. Everything is number for it, without any physical meaning. Clear? So the updates of the weights will happen corresponding to this numerical values. Okay? It will not treat, say this is thrust, say this is velocity. Okay? So we understand because of physics that, okay, fine, 0 velocity corresponds to 100 RPM maybe, 1 velocity corresponds to 1100 RPM. Okay? But we know that the neural network will not treat it that way, right? It will not be like, okay, fine, if it is 500 thrust, it will not be that, okay, fine, the velocity should be somewhere in middle, near 0.5. No, it will simply consider this value numerically will dominate the updates, right? So you don't want that to happen, right? So in that case, it's preferred that you normalize the inputs that you get or that you're using. Okay. Now similarly, if you're using these 3 terms for reward function calculation, okay, say this is term 1, term 2, term 3, and your reward function is -t1, -t2, -t3, right? Just by the look of it, you know that the reward function will be dominated by t2, right? Because numerically that is the most high value, right? Or maybe by t3 as well because it has negative values. So T1, say the reference velocity or the velocity that you have being the most important, say this is the most important parameter you have, right? It will have the least weight in the reward function, right? So now you try to keep adding weights to it, W1, W2, W3, right? And then you will have to tune those weights, right? Those coefficients of the reward function, you'll have to keep tuning in them, right? When you do that, you might not get a very you might not follow most efficient path, right? So for that, what you can do is simply normalize these, right? Either in a scale of -1 to 1, 1 to 1, anything. Basically normalize it so that everything comes in the same scale. Got it? These practical considerations, okay, again, let me remind you that are not theoretical, okay, in the sense they don't have theoretical proofs for it. However, they come from an implementation point of view. Right? Clear? Okay. Yeah, we will talk about the other things, shared replay, double critique methods, in the coming algorithms as well. Yes, okay. And in exploration, right? We have to encourage exploration in methods that don't inherently explore a lot. Right? You will see in the coming lectures that there are methods that inherently prioritize exploration as much as reward accumulation. Right?